Hi everyone, so this is section 2.4 and we're going to talk about zeros of polynomial functions. All right, so we talked about this before, that a polynomial function that has a degree n can have at most n real zeros, right? Now those zeros can either be rational or irrational numbers. So for example, if you've got this function here, you factor it, and you see that the zeros are -3 or 2/3, right? Both of those are rational numbers. However, if you've got this function here, x squared minus 5, and let's say we set it equal to 0, x squared equals 5, x is plus or minus root 5. So that has two zeros that are irrational, right? So when we say it can have n zeros, it could be either rational or irrational. Okay. So when you have a polynomial that is not very easy to factor, we have to figure out a way to still see what the solutions are. That's what we're going to talk about today. The way in which we're going to do that is called the rational zero theorem, okay? And what that does is it uses these numbers p over q in order to narrow down which numbers could possibly qualify as zeros of a function, right? So when you have your polynomial, the very last number in the polynomial, basically the constant, right, that has no x's, that gives you your p's, and the leading coefficient, which is the coefficient of the term with the highest exponent, gives you the q's, okay? All right, so let's take a look at how that works. So here it says list all possible rational zeros of each function. Now this is a cubic function, which means it has at most 3 zeros, right? One thing you can do is you can plug in every single number in the world and see if it works for this as a solution, or we can narrow down our choices. So here's what we're going to do. From this number, we're going to get p. From this number, which is a 1 here, that coefficient, we're going to get q. All right, p happens to be the coefficients of that number 4. It happens to be the factors of that number 4. So what are the factors of 4? 1, 2, and 4, right? Because 1 times 4 is 4. But also, -1 times -4 is 4. So each of these could also be their plus or minus version, right? So plus or minus 1, plus or minus 2, plus or minus 4. So we say it's plus or minus 1, 2, or 4. Q are the factors of 1, which is just plus or minus 1. Now, P over Q is equal to all of the P's divided by each of the Q's, right? So you take each of the P's and you divide it by each of the Q's. So this will be plus or minus 1 over 1, which is 1, 2 over 1, which is 2, 4 over 1, which is 4. So right now, these are all of the possible zeros of f of x, okay? So how many numbers are there here? 1 and -1, 2 and -2, 4 and -4, so 6 possible numbers. So basically, if this has any real zeros, it has to be one of these 6 numbers. So for example, 3 can never be a solution, right? 7 can never be a solution. Okay. So there is this thing called Descartes' rule of signs. That is yet another way to narrow this down even further, but I'm not going to cover it this year because we're going to have other ways to narrow down our search. So I'm going to, just skip that altogether. Okay, let's talk about complex zeros, okay? The fundamental theorem of algebra says that if a polynomial has a degree of n, that polynomial has to have at least 1 zero in the number system. So for example, if you have, a function like this, f of x is equal to x squared plus 3, that looks like this, right? It crosses the y-axis at 3. Now that never intercepts the x-axis. So one might say, okay, this has no x-intercepts. It has no zeros. But you know what? That's not the case. The fundamental theorem of algebra says every single function has to have at least one zero. So in this case, it might not have a real zero because it doesn't cross the x-axis, but it definitely can have imaginary zeros, okay? All right. So if that's the case, if every single function has to have at least one zero, that means sorry, 1 second. Okay. That means it has to have at least that many linear factors. Okay? So if something has to have at least n zeros, then it has to have n linear factors. Okay, so that's the linear factorization theorem. It says a polynomial of degree n has exactly n linear factors. And furthermore, you can write any polynomial in terms of its linear factors and what we call irreducible quadratic factors. So if a function has zeros which are imaginary, they come from quadratic functions that cannot be factored. So for example, suppose you factor f of x and you get x plus 2, x minus 1, and then x squared plus 3. These two give you real zeros. This one gives you an imaginary zero, right? Now, what is that function? This is a quadratic function. Whoops, I meant to highlight that. This is a quadratic function which cannot be factored anymore. It cannot be reduced anymore. So we call this an irreducible quadratic factor. So if there are imaginary zeros, that's the sort of thing you need from which they come. All right, that was really bad grammar. Forgive me. All right, so take a look at this one. This is a mega function, right? We're going to factor this function right now. We're going to use our P over Q to guide us, right? So what's P here? P is all of the factors of this number, 24. So it's plus or minus 1, 2, 3, 4, 6, right? And once I get to 1 like this, where 4 times 6 is 24, then it's, okay, 3 times 8, 2 times 16, 1 times, 12, 1 times 24. So that's P. And what's Q? Plus or minus 1. So that means P over Q is just the same as these numbers, right? So it's plus or minus 1, 2, 3, 4, 6, 8, 12, 24. Okay, so how do we do this? In order to start factoring this, we have to pick the one here, which is a zero of this function. You know how we do that? You basically, okay, so how many numbers are there here? 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 numbers. So what we have to do is we have to do synthetic division with every single one of these until we get one that gives us a zero. And I know if I was in the room with you, I would see all of your eyes bulging out. But you know what? Don't fear, because we're going to use a little bit of a shortcut. Okay, so what we're going to do is we're actually going to graph that function right here. All right. 1 second. Okay, so that's the function over there, x to the 5 plus x to the 4, etc. We graph it, and look at this one. You see that it has 3 zeros. And if you look closely, these zeros are all numbers that we got in our list, right? So we're visually just going to pick one of the zeros that we see here. I'm actually going to pick this one, -2. right? So I'm going to start doing synthetic division with that number, -2. So let's do -2. And we have 1, 1, -13, -23, -14, -24. So here 1 comes down, -2, -1, 2, okay, -11, -22, sorry, +22, -1, +2, -12, +24, and I got a 0. But I already knew that, right? That I would get a 0 because it's one of the zeros. So now what I have from here is x plus 2. And remember, these bottom numbers give me the coefficients of the depressed polynomial. And if I started with x to the 5, now it's 1x to the 4 minus x cubed minus 11x squared minus 1x minus 12. Okay, so now I need to factor that x to the 4 polynomial, right? How am I going to do that? Well, I basically need to do the whole process again. However, what I can do is I can go back to the graph and pick one of the other zeros. I picked -2 already, so let me pick one of the other ones. I'm going to pick 4 this time. So I'm just going to work on this one. So I go 4, 1, -1, -11, -1, -12, and I do the whole thing again. 1, 4, 3, 12, 1, 4, 3, 12, and I get a 0. So now let's see what we have. I had x plus 2 from before. From here, I have x minus 4. And then now it's x cubed plus 3x plus 3x squared plus x plus 3. Okay, now again, I need to factor that cubic polynomial in blue. I can either do it with synthetic division again, or once I get to the cubics, I want to see if I could factor by grouping. Well, this one I can factor by grouping. So all I need to do is split this up. So what I've had here from before is x plus 2, x minus 4. And when I split that up, I can factor out an x squared, and I get x plus 3 plus 1 times x plus 3. So finally, if I factor all this now, I get that k of x is equal to x plus 2, x minus 4, x plus 3, and x squared plus 1. Okay, so here we go. And I can't factor that anymore. So let's see what we've done. We have written k of x as a product of linear factors, 1, 2, 3, and an irreducible quadratic factor, right? That's a quadratic term that cannot be factored any further. All right. Next, it says, you know what? Too bad if you think you can't factor that any further. We need you to. So now we need to write k of x as a product of just linear factors. Well, what's standing in the way is that term x squared plus 1, right? That's what we think cannot be factored. Okay, so it could have been factored if there was a negative here, right? So if I have, a difference of squares, x squared minus 9, I could factor that, right? How would I do it? I just take the square root of the x, I take the square root of the number, and I do minus plus, okay? So if only I could make this into a negative. Well, guess what? I can. Who says I can't write the plus as a minus -1? Is that not the same? It is. But now I have a square, possibly a square with a minus in the middle. So now I can factor it. So what I'm going to do, same way, take the square root of the x squared. I get xx minus plus. Now I need the square root of -1. And what is the square root of -1? I. So that's plus or minus I. So now k of x becomes x plus 2, Ugh, my pen. X minus 4. X plus I, X minus I. Oh my pen. Okay, I'll have to rewrite that. 1 second. All right, let's rewrite that gibberish. So this is equal to X plus 2, X plus 3. I'm sorry, X minus 4, X plus 3, X plus I, X minus I. Okay, so that is in linear factors. And now if I want to list all the zeros, well, that's just X equals -2, +4, -3, plus or minus I, and count them. That's 5 zeros, which is what the fundamental theorem of, which is what our theorem said. Okay? All right. So let's move on. Write a polynomial function of least degree with real coefficients in standard form that has cube root of 5 as a 0. All right, so how do we get cube root of 5? It comes from taking the cube root of a number. And when do we take the cube root of a number? It's when you have x cubed equal to something. Okay, so since this is a cube root, what you're going to do is you're going to say f of x is equal to x cubed minus 5. Okay, x cubed, this number, minus 5, this number. Okay, well, let's see if that actually works. If we solve that, do we get that same cube root? X cubed equals 5, x equals cube root of 5. Okay, so yes. All right, so for example, if you wanted the 0 to be the 5th root of 2, then we would say f of x is equal to x to the 5 minus 2. Okay? All right. Next, we want to write a polynomial function of least degree with real coefficients in standard form. That means, written out with decreasing order of exponents, that has -1, 2, and 2 minus I as zeros. Okay, so here we have a complex number as a 0. Well, the thing with imaginary numbers is they always come in pairs. So you can never have only 2 minus I as a 0. If you have 2 minus I, you also have 2 plus I as a 0. Okay, so what's our function going to look like? Each of these gives us a factor. So -1 gives us x plus 1, x minus 2, x minus, here, let me put that in brackets, 2 minus I, and then x minus 2 plus I. What we have to do now is multiply all this out. Okay, so let's start with just this. That gives me x squared minus x minus 2. Here, I'll show you an easier way to do this. We're going to distribute these negatives. So this one is going to be x minus 2 plus I, x minus 2 minus I. And then we're going to put the parentheses over here around the x minus 2. Okay, we can do that. That's the associative property. We're free to do what we want. So look at what we have when we do that. I have a plus b form, and then a minus b, right? That's basically a plus b, a minus b. So I can multiply it like I would a plus b, a minus b. So what I get here is x squared minus x minus 2. And then here, I get a squared minus b squared. Okay, so that's x squared minus x minus 2 times x squared minus 4x plus 4. And what's this? Minus -1 is +1. Okay, so x squared minus x minus 2, x squared minus 4x plus 4. And then you have to, just multiply this out. All right, and I'm not going to waste your time on the screencast. I know you guys can do that on your own. Okay. All right. Lastly, we have a couple more problems here. All right. We can use synthetic substitution with complex numbers as well as with irrational numbers, right? So you don't have to do synthetic division with only real and rational numbers, okay? So take a look at this one. It says, write this polynomial as a product of linear and irreducible quadratic factors. So basically factor this, right? Well, let's see. We have to have one way of grabbing one of the zeros. This is a simple enough equation that I don't need to graph it like I did with that x to the 5 equation. I could just find one of the zeros very, very easily by setting this equal to 0. X cubed equals 3. So when I take a cube root, x is cube root of 3. So that's one of the zeros. Now I want to do synthetic division with cube root of 3. Okay, on x cubed minus 3. So I have 1, 0, 0, 3, right? X to the 3, 2, 1, 0. Okay, 1 comes down, multiply cube root of 3, cube root of 3. Multiply by this, and I get, this is the cube root of 9. So cube root of 9. Multiply again, I get cube root of, I'm sorry, this was supposed to be a negative 3. Cube root of 27, which is 3, and when you add them, you get 0. So what I have now is this gives me x minus cube root of 3. And then I have 1x squared plus cube root of 3x plus cube root of 9, okay? And this is the irreducible quadratic factor with the linear factor. So this entire thing is the factored form of x cubed minus 3, right? Who says we couldn't have irrational coefficients? Okay, so we did one with irrational numbers. Let's do synthetic division with some imaginary numbers now. All right, we want to find all of the complex zeros of this equation, given that 2 plus 5i is a 0. Well, if 2 plus 5i is a 0, then so is its conjugate, 2 minus 5i. So what we're going to do first is we're going to do synthetic division with 2 plus 5i. All right, so leave some space here when you're doing this. So I have 1, negative 6, 35, negative 50, negative 58. Okay, 1 comes down. 2 plus 5i, right? Okay, add these, negative 4 plus 5i. Okay, now you have to multiply 2 plus 5i times negative 4 plus 5i. So let's see what happens. FOIL, right? So negative 8 plus 10i minus 20i minus 25i squared. Okay, so that's negative 8 plus 25, 33 minus 10i. Okay, stick with me and something beautiful will happen. Except I feel like it should be a negative 33. Okay, sorry, I made a little typo here. This should be a positive 25 I squared. So that's negative 25 minus 8, negative 33 minus 10i. So that's a negative. So here I get 2 minus 10i. And now I need to multiply 2 plus 5i, 2 minus 10i. So that's going to be 4 minus 20i plus 10i, so that's minus 10i. Minus 50i squared is plus 50. So that's going to be 54 minus 10i. And that, when you add, will be 4 minus 10i. Multiplying again, 2 plus 5i times 4 minus 10i. I get 8. And then negative 20, positive 20, they go away, right? The i's go away. And then minus 50i squared. Oh my God, that's 58. What? How did that become real? Okay. Now, I want to do synthetic division again with this 0 and these numbers. Okay, bear with me. This is going to come out really, really cute. So 2 minus 5i, 1, negative 4 plus 5i, 2 minus 10i, 4 minus 10i. Let's do this. 1 comes down. 2 minus 5i. Oh my gosh, the 5i's go away, so we just have negative 2. Next, multiply. Negative 4 plus 10i. Oh my gosh, the i's go away. I just have negative 2. Next, negative 4 plus 10i. Oh my gosh, they all go away. I have 0. So what happens? Doing it twice, the coefficients switched back to real numbers. Tell me that's not cool. Okay? Now, what is this function reduced to right now? I have 2 plus 5i, 2 minus 5i, and then x squared minus 2x minus 2. Now I need to factor this guy. Except, wouldn't you know it? That can't be factored. Plot twist, I have to do quadratic formula. All right, so let's do the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4a times c all over 2a. So x equals 2 plus or minus root 12 over 2. 2 plus or minus 2 root 3 over 2. So x is 1 plus or minus root 3. Okay, now I have completely forgotten what it is that I was supposed to find. Oh yes, I was supposed to find the zeros. So what are the zeros of this function? X equals 2 plus 5i, 2 minus 5i, I can write it like this, and x equals 1 plus or minus root 3. Okay? X to the power of 4 has 4 real and complex zeros. All right, so much for that section, and now you can go ahead and start on your homework.